let's assume there's no problem between sending signals. So we're going to look at the next stage. How do computers actually move information? And there are 4 techniques. I'm going to mention the 4 of them now briefly, but you should know, and if you don't know it, well, hopefully you will know them very quickly. The first technique is known as message switching. All right, the message switching is the first technique that computer companies started doing. So when computers started back in, they started back in the 50s, 60s, and then computer companies started sending information. The first technique they used, they called it message switching. It takes their full message and send it to the nearest computer. And at the time, the nearest computer, they only had radio transmitters. So they have a transmitter that sends a message and a receiver or an antenna that take the message. But the message is large, so this file that needs to be sent is the entire file. We read it 1 byte at a time, send it all the way there, and here we store it on something called external storage device, which is a tape. At the time, there were no hard disks, but then hard disks were started being used. So that's the way how message switching works. It goes from one machine to the other, transmitted. This transmitter can go 100 kilometers, can be 1,000 kilometers, whatever. It depends on how strong the radio transmitter is and how far it can go. But then it's received. Once it's fully received at this machine, then it's transmitted to the next machine. The same thing. So, and it has to be stored in an external storage device. You should know by now that memory, there are 2 types of storage memory. One is called main memory, and one is primary memory or main memory, and the other one is auxiliary memory or secondary memory. That's tapes and hard disks and other storage devices. Difference between them, electronic memory or main memory is electronic. It's electricity going through these tiny, minute electronic switches, and it's so fast. Electrons flow through wires almost at the speed of light, almost. Close, very close to the speed of light. While if you are storage, outside storage or secondary memory is very, very slow. It's comparing main memory to auxiliary memory. It's like the difference between traveling in a rocket and traveling on a horse cart. That's in ratio. So hard disks are mechanical devices. Tapes are mechanical devices. Anything mechanical is way too slow for main memory. So, and that's one of the reasons why this technique is so slow. It might take 15 minutes to transfer a file, maybe half an hour, transfer a file from one place to another, and it's stored onto the tape or written onto a hard disk or any auxiliary storage device until it reaches, and we keep doing that. It might go over 5 or 6 or 8, transmissions. And if something goes wrong while you're sending this file, if 90% of it is received and then when there's 1 bit error, you say, hold on, there's an error, start again. You don't step back a couple of bytes and continue transmitting. So it can get even slower if there are errors, if there's noise in the air or electromagnetic storms or whatever. And then eventually the file gets there. So that's the first technique, which is no longer used. But that's how computer companies started sending information. So back in the 70s, somebody thought of another idea. He said the main reason here is that we cannot use main memory to transfer information from main memory to main memory to main memory. If we could do that, it would be much faster. And the reason we can't do that, because the message is too big. So he said, let's break that message into smaller units. And that's what they did. And they produced the next technique, which is in use today. It's called datagram switching technique. Datagram is similar to the message. It's a development of the message technique. All they did, they said, okay, well, if you have a file or a message you want to send, break it into small units. We call them datagrams or packets or cells. It doesn't matter what the name is. But at that time, there used to be something called telegram. I don't know if you've heard of telegrams. In the old days, if you want to send a letter in the post, it might take a week or two to reach. But if you want to send it by radio, you go to the post office and say, I want to send a telegram. And a telegram is a message you write and they charge you per word. At the post office, you pay for the whole letter, very little money. But telegram, no, you have to pay for word. Every word is 20 cents of, I don't know, €1, whatever it is. And then somebody starts tapping it on the radio, it gets to the other end, and it's delivered. So it's delivered much quicker. Within an hour or 2 hours, it could be there in another country, in another city. That used to be called telegram. So that's done by the post office. So when the computer companies brought this, they said, well, we call it telegram. No, of course they can't, because already somebody else has a telegram we're using telegram. So they call this datagram. So, but the main idea of datagram is that you never send a message, very large message. There's a maximum size on the message that can be sent. And the reason why, now they can fit in main memory of every router, every device they go to. So it's a continuous electronics, no more secondary storage. So it goes from one memory to memory, keeps flowing through those wires, and that's the speed of light, and it can get from here to Australia in a second or less. So that's the major development in speed in communication, the datagram switching technique. So this is, if you have to describe it, maybe 4 or 5 statements describe it. Then we see what features does it have and what are the problems with it. But this is the way it works. You take a message, every message is broken to smaller units, we call them datagram. Every datagram, we put a header on it. We add some information onto it that are not part of the message. And this is one advantage. You have to carry more information, not just the user information. Now we have to carry extra information. We call it the header. We put it ahead of the data, of the datagram. So we call it the head of the datagram. And what do we put? We put the source address, destination address, and a sequence number, 1, 2, 3, 4. So every packet we put on it. Say now we put the IP address and of the sender and the IP address of the receiver. They both go on it. And if you forget, if you don't know, if you get mixed up, just think of the post office. This is like sending a letter in the post, in the ordinary post, not the registered post. So anytime you want to send a letter, where you have 10 letters, you want to send them to your friend in India or in Australia, and you want to send one every day. Think of it, we want to send one letter every day. So we take the envelope, you put the letter in there, the message, and you write the destination address, and on the back you write your address, the sender's address, and if you want your friend to receive the 10 of them, just mark them 1, 2, 3. This number means nothing except at the very end. Now, in computing, we give those to the nearest device. Of course, if you are connected in a network, normally in all textbooks, that's what networks look like. When we draw a network, normally that's what a network looks like. These are the devices of the network. Let's switch the light off would be better, is it? Is that what you are saying? Okay, can you manage the light here for us? So, yeah, switch that and maybe switch it. It's better? Now I can see you clearer. But maybe you can see this clear. This should be actually, is this better? Oh. Now, this is the infrastructure of a network. Any textbook you see drawing a network, normally You might, yeah, mostly this is the diagram, the way it's, that means these are all the devices that move the information. These are routers. In some places they call them switches. And the users are always drawn outside, on the outside. That's not normally how things really in the real world, but this is a nice way of seeing it. So maybe you and your neighbors are all connected to the same router and so on. In every neighborhood, they're all connected to the same router, and one router connects you to the next and so on. Because remember, the best way to communicate with somebody if you have a direct link with them. Or there are two ways to communicate. You either have a link to the other person, direct link, a wire connecting your machine with your friend's machine, and you can send as much data as you want, as much as that link can carry. That's one way, but that's not really practical. So if you want to connect to 10 people, you must have 10 cables. You can't even plug 10 cables to the back of your computer. And if you want to talk to everybody in the city, you must have a direct link with everyone. That's not really a practical way of doing it, but that's one way of communicating. It's called point to point or link to link. Machines on either side of a link, and they just have that link to themselves. But that's not possible to communicate with anybody. The other technique is to broadcast. What most wireless networks do, and some wired networks as well. So if we all have computers and I want to send a message to you, I send a message and say, in the packet frame, this is machine number 17, and I send it. Everybody gets the message, and ignores, because that's not their address or their number, but machine number 17 says, oh, that's for me. I'll take it in and pass it to the user. The user send back this message. What they do is they broadcast. So you can hear everybody. So that's the other technique. It's a multi-point technique. It's like broadcasting. You just broadcast to everybody, and only the intended party take the message. This is not good either. This has few little problems, and you should know these things. I'm just refreshing your information. If you are broadcasting, then if I'm transmitting and you want to transmit, you have to wait until I'm finished. And then if someone else wants to transmit after that, then they have to wait for me to finish and you to finish. So the problem with broadcasting is that the delay. You have to wait for a long time before sometimes it's your turn to transmit. Why? Because we're all sharing the same transmission time in broadcasting. And therefore, it's generally very slow. And if it gets too many the sharing increases too much, then it becomes impractical either. So those two techniques are the two extremes. Either everybody has their own link, if you want to communicate with them, that's called point-to-point communication, or broadcasting, and that's multi-point. Switching is the in-between technique that, like the telephone companies, you can talk to anybody in the world, you don't have a direct link to them, and you're not broadcasting. But they use these switches to connect you only to that person temporarily. Once you finish talking, they can connect other people. And that's what switching really, where the name switching came from. So we're going to be doing how the datagram switching technique works. So now, for example, this user here wants to send a file to that user there, could be on the other side of the world. All they have to do, break the message or the file into smaller units, we call them datagrams, add a header to every datagram and put on it the source address. Of course, there's a lot more information, but for now, you need to put in the source address, destination address, and a sequence number. A lot more information, we'll talk about it as we need it later on for error detection or for flow control and so many other things. So, and that's for now, that's what we need. And all you have to do, just give all the packets to the nearest device. Just give them to them. Just send them 1 or 2, 3, 4, give them all to the router. And every router looks at every packet independently, just like the post office. They don't take the letter that you're sending to your friend in Australia and say, oh, this is the same guy that sent yesterday. No, they don't think of it that way. There's no relationship between the letter you post today to Australia, to the same friend, and the letter you post tomorrow to Australia to the same friend. Post office don't look at them that they are related. Yesterday's letter, they could have picked it, they said, oh, this is going to Australia. Of course, we don't have a direct link to Australia. Same here, we don't have a direct link with your friend at the other end. So they'll send it to the nearest country in that direction towards Australia. They might say, hey, let's send it to London. From London, they'll push it towards Australia. So, and then tomorrow's letter, they pick it up and say, oh, this guy's sending a letter to Australia. Okay, let's send it. There's, storm over London, all flights are stopped. Let's send it to Rome. The same packet, some of the first packet, let's say this route, say, where's the best route? So the route is picked for every packet independently by every router. For example, this router might say, oh, you want to go to that address there? Let me send you to this one here. So packet number 1 goes that way, packet number 2, packet number 3, they all go in this direction. And then maybe this router notices, hey, things are slowing down here on this side. Let me change to another direction. So it might send number 4, 5, and 6 in this direction. Receives the packets. This router might say, oh, number 1, I know where you are, so I'll forward you this way. 1 and 2 might go this way. If things are slow, it might send number 3 in this direction, and number 3 will arrive in that direction, and so on. So same with this one here. It might send number 4 in this way, but 5 is, and it might send it in this direction. So the point is, just as your post letters, that you post them and they might follow a different route, but eventually they'll all get there. And the same with the datagram. They might go in different directions, they might follow the same route. Will eventually get to the final destination. So when they get to the last router and forwards them to the last machine, the user, the machine will look at them and will look at the headers information and say, all right, first, maybe they're out of sequence. Maybe we got number 1 and then 3 and then number 2 and then number 4. So it will put them in the right order. And then it will actually remove all the headers, get rid of all the headers that were inserted by the sender. See, these headers were inserted by the sender. They're deleted by the receiving machine and put all the packets together in one file, and there's the same file there is now transferred to the other end. What's the main thing about this? It's the speed. There's no, devices don't have hard disk to put information onto it, or tape, or any external storage device. We just use main memory. Main memory, it means it's extremely fast. Electricity starts from your machine, goes to the nearest, to the main memory of the nearest router, to the main memory of the next router. So this packet is jumping through main memory so fast at the speed of light, and it ends up in Australia. And this is the big revolution in speed in communication. So the main idea is datagram. And what's the main idea of datagram that made it so fast? Packets are so small, they fit in main memory. But there used to be a problem with main memory. It used to be very small. Now it's much bigger. But we still use datagrams, but we have now bigger sizes. Like a datagram now might have a size of 3,000 bytes. When we started first, maybe 50 bytes or 100 bytes. Now it can go up to 3,000 bytes, and they fly in one after the other. And even if the transmitter is slow enough, it can actually store the next packet or next 10 or 20 packets in its main memory. Now main memory is getting bigger and bigger and better and faster, but we're still sending information so fast. And that way, with the datagram switching technique, we were able to transfer information so fast. And this started in the 70s. And it's been improving all the time. Now, looking at it, there are a few things I just want to remind you. These links that are connecting all these devices are they dedicated or shareable? They're shared. Not just your data is going this way, also data that this guy is sending to this guy. It might send it straight that way or go in this direction. So every link or every channel, whether it's a cable or a radio transmitter, is sending packets that belong to different users from different sources to different destinations. On a street, they don't all belong the same, but they all get onto the runway and one after the other, and then some of them get off the runway or the motorway at the next exit, and some of them continue a little bit further. And same with this one, say packets going from here, it's just same as the post office. All the posts are going to Britain and to France and to Australia. They all put it on the flight to London. It gets sorted out. Oh, this one's staying here in Britain, the rest of it, this is going to France, and this one is going to Australia. It gets sorted out at the next location. And if you notice that maybe you can consider those routers are like airports, hubs. You jump from one flight to the next at the next airport, you get sorted out, sent to a different direction. And as you notice here as well, just these things I need you to keep in mind. Every packet is independent. It does not, bear any relation as far as the network is concerned with the packet before it or after it. Everyone is treated separately and independently, just like the post, how they treat each individual letter. These are some of the good things about it, the speed. Some of the bad things, and maybe sharing the links is much better than dedicated links. Why? Anybody knows what's the advantage of sharing over dedicated links? Cheaper, because 10,000 people can use this link. If you want to have a dedicated link, only one user can use it. And that means if you have to pay for it, one user has to pay a lot of money for one link. But if the link is shared by 10,000 people, then it's going to be cheaper for everybody. And this is the technique that's used by the internet today. So this technique is still in use, and it's probably the most used technique. This is the datagram switching technique, because it's so good, I guess, right? Possibly the only reason is that it's very cheap. Because with this technique, just like the post office, remember, if you send a letter to somebody in Australia and the letter is lost, and your friend in Australia never got it, does the post office tell you? No. Or if the letter is delivered, does the post office tell you that the letter has been delivered? No. Same as in datagram switching technique, there is no acknowledgement, positive or negative. This technique. So it's not really, you don't know whether the information will get there or not. Most of the time it will get there, but it's not definite. The other thing is that there is no error detection in it. But if you send a letter and then the inside of a letter change, remember, every message you send in computing is just a list of ones and zeros. What happens if there's a bit of noise or magnetic field and the one is turned into a zero or zero turned into one? This datagram switching technique does not do any error checking, and it does not correctly. So it doesn't check for errors. It doesn't acknowledge your message, whether it's received or not received. And sometimes, because the line is shared, and every line has a capacity, like every road. A road can carry 10,000, maybe 1,000 cars. If you send 2,000 cars at the same time, it would stop. There'll be no traffic going. Same with datagram switching technique. We have a network. It has a certain capacity of links, and it can, for example, carry maybe 10,000 packets reasonably fast. But what if now we have 20,000 packets, or 15, or 25,000? Users decided, okay, your neighbors decided to download files and send and upload videos, then it's going to increase the traffic. What happens when you increase the traffic? There's something called the quality of service. Quality of service refers to the speed. How fast do things go? It refers to other things, we don't lose material and all that, but mainly it refers how quick do we get the information. And if you are watching a video using the datagram switching technique, if you might watch it without any interruption, but not guaranteed. If your neighbors were, like you start watching a video and maybe 15 minutes later your neighbors start downloading and uploading videos and things like that, or communicating a lot, then it's going to increase the traffic in your area. It's going to slow delivery of information to you, and you might start noticing delay. And you know, it might happen to you many times. If you're watching a video, you're happy for 10-15 minutes and then start stopping and slowing down and interrupting. We say quality of service is poor, and these things are really slowing down. And the main reason is there is a lot of traffic. And the main reason why there is a lot of traffic, because datagram switching technique does not guarantee the quality of service. And why? How come? You might be asked why the datagram switching technique cannot guarantee, because it can never say no to any data to be transferred. And as you noticed when I started explaining here, we said you have a file to send, break it into packets, put the header and give it to the nearest router. You don't ask the router, can I send you the data? No. And the router can never say no to you. You send it to the router has to deliver. This is very much like the post office. You have a letter posted. They don't say to you, oh no, maybe today we will not. No, there's a box there, you drop it. It's their responsibility to take it from there on. So this is called datagram switching technique, and this is the technique that's in use today. Right. Now, there are two other techniques that are in use, because when the computer companies started back in the 60s and in the 70s, they changed it to datagram switching. Jealous, other companies, and they're the telephone companies. Telephone companies have been around for 100 years before the computing. So maybe about 150 years we've had our first phone. The telephone companies say, hey, this is our area. You guys are coming in communication from us. Yeah, we are the experts. We have the experience. We can do it better than you. So, and they did. And they want, it's all money, of course. That's all they want to get, you know, make some money out of this, because there is a lot of money in communication. So how did they do it? I'm going to tell you how the old telephone systems work first. So the old systems work like this. This is called circuit switching technique. The circuit switching technique is the old technique that's used by the old telephone systems. And how does it work? Okay, every city, there are many streets, of course, in every city, and squares and all that, and when they started putting phones, all the houses, for example, on a street, they have telephones. I'm just going to have this shape here to look like this is a phone. And in every street, in every city that has phones, there's a box somewhere up or down in that street. Every street, in every city, in every, you know, around the world, there's a box. And that box is called switching box. And that's where the word switching came from. So, switching boxes. Switching box just has lots of switches in it. And the boxes are still there. But in the older days, they were mechanical switches. They move, they physically rotate to connect any two wires together. But now they are electronically connected and they operate. But the boxes are still there. And now they are electronic boxes like routers or switches. And every phone is connected to the box. Every phone in that street is connected to this box. And the same in every street. There are so many boxes in every city. It's also on the houses, companies or offices. There are lots of phones, and these phones are all connected to the neighboring boxes. And they still do. And right now, maybe even with the telephone, with the internet, you need to be connected to a router up the road. But still a router, it does pretty much the same job. But that's how telephone companies used to work. And also, every box is connected to so many other boxes in the city. They can actually connect you to talk to anybody in the city. You don't have to have a direct link with them, but if you want to talk to somebody, they make all the required connections that you can communicate with another person. So, and then this one here has another box that's connected to that, and another box to this one, and this one also has many other boxes. So all the boxes in the city are connected together. And from one city to the next city, there's a connection from all the cities to another country. So connections is just big. It's a big network. But it's been around for 100 years, for 150 years now, and it's getting better and better. Now, this is how it works. If you want to call somebody, if this phone here wants to communicate with that phone, it needs to know it's the destination address, but in this case, phone number. So you need to know what's the other side, your phone number that you want to call. And you pick up your phone, let's say this phone here, you pick up the phone and start dialing the number. So first, this circuit switching technique, before you can send data, you must do another thing, and they call it call setup. So it has an extra step that needs to be done. Before you start sending data, even computers that we use to connect on the modems to talk to other computers, first you must call the other computer. So that's called the call setup phase. So so the circuit switching actually consists of 3 steps. First is call setup. If the call setup is successful, then you go to the next stage, which is called data transfer. Number 2, data transfer. And when you finish sending your data, you do the 3rd and last step, which is, anybody knows what it is? Call clear. Finish the call. This is what you do on your mobile phone today. You want to talk to somebody, you don't pick up the mobile and say, hey, Tom. No, first, before you can talk to Tom, you must dial Tom. You do the call setup. You dial it and start ringing, and when it starts ringing and Tom answers, now that's the step done. The call is set up. Now you can talk to Tom or send data to Tom. If it was an app, it's calling another app on the phone. But this is how the old circuit switching technique worked. So now the first phone picks up the call, and start dialing this number. Let's say whatever this number is, 453, right? So this number goes there and start rotating this switch. So it will connect it to the suitable box, wherever that phone is. And let's say this one here is connected in this direction. So this rotates, so this is connected with that. So now this is the connection is made to this box. Now this box, the switch also starts rotating based on the numbers you've dialed until they connect you to one of the boxes. And this will be connected to maybe 30 boxes or 100 boxes, but it'll pick one of them, and this is the one it'll pick because it's bringing you closer to that phone. And now the switch here, it can connect you to this one there, and the last switch here will actually connect you to that phone. And as you can see, and then starts ringing from this point. The phone starts ringing. And if somebody picks up the phone or answers the phone, or if it's on a computer, they say, hey, somebody's calling you, accept or refuse, you press accept. Now you have the right to accept or refuse. So now, first thing that you notice, the difference from the datagram. With the datagram, you don't have to make a call at all. Just take data or datagrams, put the source addresses, and send it to the nearest router. The network will take it. Here, no, you can't even start sending until the network takes from you, accepts you, and then the final destination will also accept you. So the call setup has to be done. So that can be, is it an advantage or a disadvantage having to make a call? Is it better to do it without calling the other part? I want to send you data. Is it better to send it to you directly without calling you, or according to the datagram, or according to this one, I must first call you, send you the data? What do you think?
It's better because
It's what?
it's better because
Yeah, it's a good answer. But is it the right answer? Sometimes it's better. It depends. Don't forget the word depends. I'm going to stick it here. Big word here. Okay. Right. But you won't forget the exam, right? If you're asked, is it better to have a call setup or is it better not to have a call setup? Don't say it's better to have. Unless if you give the reasons for it, right? And you give both reasons. What's the advantage for this and advantage for that? Now, but this is the way it works. Whether we like it or not, this is the way phones work. So, and this is the circuit switching technique. Now we start talking. But now, as you can see, the phone is connected from this end, continuing with those two wires all the way to this phone here. And this is like an electric circuit, all the way from the source phone to the destination phone. And it's dedicated. This is dedicated to the user. Even though it wasn't dedicated before, but after we made the connections with the setup, now this line just carries information from this phone to that phone and no other phone. So now this one is dedicated, and this is the only technique that uses dedicated. I ask you to describe datagram switching technique or message switching or the next technique that we call virtual circuit. None of them has dedicated. This is the only one that has dedicated. Now, the question, is it better to have a dedicated link like this or a shared link? What do you think? It's better, this is a dedicated line. This connection from this phone to this phone is dedicated only for those two phones, for the duration of the call. So you can send them. So is it a good idea, or is it better to use the shared, like the datagram, where we share the links? This one. The good answer, another good answer, but it's the wrong answer. Why do you think it's dedicated line is better for a call? Give me one reason why you said this one is better. No, we can connect them and they can still be shared. Why do you think dedicated as he's playing? That means it's not necessarily correct, but let's assume he's correct. Dedicated is better. Why do you think dedicated lines are better than shared lines?
Because you're sure you're connected to the person. You can refuse, the person who's receiving can refuse it.
Okay, because it gives the receiver the right to refuse. Okay. Any other reason why dedicated lines are better than shared lines? Anybody? Yeah? Yeah, if you have a dedicated line, that means no one else is sharing. Remember, every line has a maximum capacity, maximum how much data you can send through it. If it's dedicated to you, then the total capacity is yours. There's no delay. There's no one else sharing the same link. It's like you having a motorway just for yourself, but you have a BM or a Merc or something that can drive really fast and stop, do whatever you like. Nobody is sharing that link with you. So that's the advantage. Speed, good quality of service. If you want to watch a video, this is the best way to watch it. Get your own link. But what's the advantage of sharing, or what's the problem with this? With datagram, you can still have a connection, but you're sharing it with thousands of others. What's the advantage of sharing, Sarah?
So with this thing, like, suppose you're not the lucky one who has a connection, you have to wait for a long time.
Yeah. So here, remember, if you have this link and there are other people that want to use it, let's say there's another user here that wants to call another user there, and they need to share this link. And if this link is dedicated and we only have one wire, then they have to wait. Also, you may have to wait before you get your call. Remember, you had to make a call, and if the network is busy, then you would have been put on a wait. And there are a lot of busy lines in the old days, in the old telephone system. But that's how it works. So this is the old circuit switching technique. The other thing about this is all one electric circuit from one phone to the other. If this line breaks, anywhere at all. If it breaks or goes loose, what happens? You lose the call completely. You lose the call and you have to start a new call. You don't just wait till it's connected, now you can resume. No, you don't resume. Anytime that link is broken, you lose the call. While in the datagram, this is the previous technique that's the one that the datagram uses to. If, for example, all your packets are going this way, this router is sending them that way, and this link breaks, you don't even know. This router will switch and start using another link, and it will deliver them, just like the post office sending your information to London. London has strike or so whatever it is. There are no flights today. No problem. It's changed to Paris or change to Rome, or so you can pick many different directions. This technique, the datagram switching technique, is very flexible with routing. Routing is flexible. And also something called robust. A robust system is a system that will continue to operate and work even or despite if this part of it is broken. So in the datagram, if you lose that link, doesn't matter, the network will continue deliver your data. So we call that a robust system. So it's very robust. Routing is flexible, and quality of service. What about quality of service with the datagram? We cannot guarantee it. Sometimes it's good, sometimes it's bad, depends on the traffic. But with the circuit switching, is it robust? It is not. If that link along the route breaks, you lose the call. Can you change the call? No. Once you're booked, you cannot change the route. So routing is not flexible. I'm just going to put the word flexible as keywords, and the answer is no. Routing is not flexible. But that's how telephone companies worked before. Yeah?
So I have a question about the dedicated work.
Yeah. Dedicated during the call.
Yes, so you said circuit switching is the only one that's dedicated per se. But
Yeah.
Isn't message switching also kind of dedicated? Because like there's one message and like it's
Okay. But that's only the way we've done it is just you're only sending one file. But who knows? You could maybe agreeing with the other side. All techniques, they actually break the packet into the message into packets, even though you don't have to do it in message switching. But they can take your packets one at a time, and then sometimes they send packets that belong to some others. Yeah, but generally they're no longer in use, and we'll concentrate on the ones that are in use. So this is the circuit switching technique. This is the old way how telephone systems work. But when they saw the communication and computing and datagram switching, then they started getting, excited and interested. So they said, hey, let's bring in our own technique. And they went and they came back with a fantastic technique, and it's called the virtual circuit. And the virtual circuit switching technique, the word virtual means it's almost like virtual reality. You get into a computer and it's like you're living in another reality, even though they call it virtual reality. Not real reality, but almost as close as possible to it. So this one here, they said, okay, this circuit switching is a good idea, but it has little problems, so let's iron them out and improve it. And they did, and they came up with the fantastic technique called the virtual circuit. And this is the technique they came up with. Here's a network. We have the same network structure, and users are outside the network connected to these routers. And let's say this user here wants to send a message to another user there. So this is the message, it's the same file, but now they said, okay, we're not going to send one big file, same We're gonna, these links are shared as well in the new technique. They're shared. There's nothing dedicated anymore. And they get the packets, they break the message into smaller packets, but before they send these packets, they send one packet. That's like the equivalent of the call setup. They have a new packet, small little packet, and it's called call setup, call request or call setup. So again, they use 3 phases, 1, 2, and 3. That's call setup. They still use the same technique, data transfer, and call clear. They like the call setup or call clear. They say it makes accounting much easier. And in a way, it's because you know who made the call. The one who sent the call request is the one you charge. With the other technique, the datagram switching technique, everybody's connected. There are no calls. Anybody can send any data they want. And that's why now in datagram switching technique, they don't charge you by the number of calls. They either have to charge you, they have to go to counting the number of bytes that you've sent, or they say, listen, forget it. It's 20 euro a month and that's it, whether you use it or not. And that's how most datagram switching technique operate. But this one here, they say, no, it's easier. We can control exactly and only charge those who make the call. So anyway, you start by sending a request. What does the call request have? It will have the source address, destination address, back to addresses now, or numbers if you like, because that's what an address is. An IP address is also a number, but IP address don't use this technique. So, but you still need a destination address and a source address. And you say this is a request. So I'm saying packet, this is just say 1, that means I'm call request. Maybe make it 2, that means call response. Somebody, the receiver can respond with number 2 or 3. 2 is I accept the call, maybe 3 I refuse the call. But it's the same packet, very small packet that goes out, and you send that, you give that to the nearest router. And every router in this technique has a table of calls, whatever. It can have 100 calls, can have 1,000 calls, can have 10,000 calls, normally about 10,000 calls on each router. It can handle how many calls this router can handle. It depends on how much memory it has, how much processing power. So it can handle 10,000 calls. You just take that as a number now. So it has a table of 10,000 records, and they're all indicating possible phone calls, and they're all at the end, they're either busy, or free. Busy, or free. So anytime this guy here, let's say this is user A wants to communicate with user B. So he puts here A and B, that's their addresses, and wants to communicate with them. So when this router gets it, it says first, hold on, can I take another call? Maybe I already have 10,000 callers. It might refuse you. But let's say it goes through its call stable saying, here's a free. I have a spot for a call. So it takes it and fills your information. A wants to communicate with B. And it says, okay, when A sent me information, see, every router has ports at the back, 6, 4, 8, 16, whatever. Says, where did this call come from? Let's say port 0, 1, 2, it came with number 2, and I'm going to send it, so it came at number 2, and I'm going to send it. I am connected to 2 routers, so which one is better? This one or this one? We'll find out later on how routing works. But let's say, okay, I'm going to send it to this one, so I'm going to send it to port number 3. And see this record here, these are all record 0, 1, 2, 3. Let's say this one is record number 48. Now that number is important. That information about that call is kept in the array on the table number 40, record number 48. And that's going to be very important. This technique, guys, is like booking a holiday and traveling on a holiday. Imagine you're in Ireland, you want to go to Australia for a holiday. So, okay, you need to book your flights. Okay, there's no direct flight to Australia, so I might say, hey, there are better chance of flights in London. So let me book one flight to London. So you call Aer Lingus, you book your flight to London. And then from London, you say, well, okay, how much is the flight to Australia? It's too expensive. Maybe I can go to Rome and from Rome I can fly to Istanbul, and then Dubai, and then Sydney. And you find this is the cheapest way. So you book each one of those first. And that's really what happens here. Excuse me. This router here is like Aer Lingus. It has all the flights and all the bookings, and it looks at stable, finds a free seat on one flight, and books it for you. And that number there, it gives it to you. This is like your booking code. And here we call it your virtual circuit code or virtual circuit number. And then it forwards it, then now it sends the request to the next router, let's say London. So this is like British Airways. They have their own flights, and they find flight number, maybe a record here, number 217. Yeah, it's free. Well, then it says A is requesting a flight, a talk to B, and I got it on port number 3, and I'm going to send it on port number 11. And this is still a request. So and sends it to this router. And this router also takes it down and books your flight and sends it to the user. And remember, each one of them, that number is important there. So the user here, maybe a message appears on their screen. There's a call. This guy wants to talk to you, accept or refuse. Let's say press accept. Accept or refuse, the message will be sent back. The same packet is sent back with another code. I'm accepting or refusing. So sends back, and this router will update here. The call is on. It's not a request anymore. And this one receives it and marks it as on. This one marks it as on. And they send this message call request back with the number here. What's this number here? 28, is it? Yeah. So they say 28. I mean, this, if you're booking a holiday, that's like your booking code with Aer Lingus. Remember, you have another booking code with British Airways. So that's what virtual circuit are. You have few virtual circuit numbers, but you only get one virtual circuit number. Now, once we say the call setup is done with the virtual circuit. Now, all the packets, you create them, and you don't put any more source address, who's token A is talking to B. No, you don't need to. All you have to do is put 28. That's the virtual circuit number, 28, 28. And of course, you need to put the sequence number. And that's it. And start sending them to this router. Now this router will look down. Any packet that comes in, it'll look and say, what's that? What number are you? 28. So it'll go down 28, say, oh, A, and you're talking to B. And you came to me on port number, whatever it is, 4, and I'm going to just forward you to number 3. So just take that packet, puts it in number 3. But it will change that number 28 to 217. That's the next booking code. Let's say if you fly to Aer Lingus and you get to London, you have now to talk to British Airways. They say to you, what's your booking code? Here's your booking code, and they enter it. Say, oh, we know who you are and where you're going, and we know what gate you came from, and go to this gate, and they'll help you. So every router along the way is like every airlines. In every airport you land, they're asking for one thing. That's booking code. We call it the virtual circuit number. You produce that, and they'll forward you along the way, and they'll send you all the packets going. So all these packets will follow the same route. But remember, like airplanes, you're not the only traveling person. The airplanes are traveling to London every day, almost every hour, and you're just one of many who are traveling. So the lines are shared. So these lines are shared, and they travel all the way, and they take you to Australia. Well, though some other passengers will go to London, then switch to a different direction, but your flights will not change. Your route will not change for the duration of this call. And then when you send all your data all the way to the other end, then either one of the two parties can terminate the call by sending a call clear packet. It says, I am A or B, and I want to terminate this call. And you send it to the virtual circuit number, and every router will go down and say, okay, this is free now instead of book. Free, and the call is terminated. Yeah.
So are the packets sent sequentially or like they send in any order?
Okay, but because the packets will follow the same route. They must follow the same route. This is not like the datagram where they might go in a different route. Routing is not flexible here. This is exactly like booking a holiday, and the other one is like the post office. Anytime you forget about them, think of booking a holiday or the post office. With booking a holiday, once you book, you're not allowed to change. If, for example, while you're flying from here to London, there was a strike and you miss this flight, you'll lose the entire holiday. You lose the entire trip. So the call is terminated. This does not have flexibility in it. But what it has a guaranteed quality of service. So quality of service is guaranteed. Why is it guaranteed? And then the datagram is not guaranteed. No, the reason is that this router will deliver you a good service provided we don't have too many calls, too many users. So now every router has enough calls that will make sure they're okay. It doesn't accept anymore. So if we have more than 10,000 calls, if we have here 10,000 calls running, and you are caller number 10,001, you say, no, sorry, I can't take it. Or maybe this router will take you, but when it asks this router will refuse, say, I'm too busy. So we might switch to another router at the start of setting up the call. But once the call is set up, then you cannot change. But the reason it provides a guaranteed quality of service is that because it can refuse, it can block new calls in order to maintain good quality of service for existing calls. So this is the difference between and datagram. Virtual circuit, it can guarantee you a good quality of service. That's what the telephone done. They said, listen, we are experts at communication. We know users eventually will want a good quality of service. We can guarantee it for them. And they do. And they do that by actually refusing any extra calls from coming online. Yeah?
I just wanted to ask, can we just...
Dedicated? No, there's no dedication. That's in the circuit switching. It's temporary dedicated. In the older telephone system techniques where the calls are temporary dedicated. That's the old one, the circuit switching. Once you establish a link in physically, that's a physical electric circuit between the sender and the receiver. While this one, even though you're sending your packets, maybe someone else is sending packets to a user here, you're sharing the same link. So there's still small packets going that belong to different users going in the same on the same channel. Yeah? Yeah, a different virtual circuit, because same as booking. If you book a flight with Aer Lingus to London, they'll give you their own booking code. But when you get to London, you booked with British Airways before you go, you booked another flight, then they give you their own booking code. So the virtual circuit changes. So when you send the packet with the number 28 in it here, what this router will do, before sending it this way, it'll change it. It'll still have the data, but instead of 28, it'll put the next number 217. So when it's received by this one, it knows who you are. And then when this one sends it, it will replace that number by the next booking. Yeah. Okay, coming back, they'll all follow the opposite direction, and it will get them to the same destination. They probably have here the number 27 and 20, the virtual circuit coming in, the virtual circuit going out, that they can actually work it out, yeah. And they also have the port number, because sometimes you might have two calls to the same person. They will be able to identify each one of them separately. Anyway, so this is in basic terminologies how it works, yeah?
So basically in virtual circuit switching, the routing happens only once during call setup, and after call setup is finished, no matter what, it won't reroute.
Exactly, yeah, the routing is fixed. So you only do a call setup at the start, and that's when the route all the way to the end is determined. In the datagram switching technique, every packet is determined, the routing is determined for every packet at every router for each packet. Here, that's it, there is no more routing. You have The routing is already mapped out for you, and you just follow that route based on whatever virtual booking code they gave you, virtual circuit number.
There's absolutely no circumstance in which you will reroute after call center.
No. It's, okay, there's a technique that was involved, improved later, but I don't want to get into it. We want the basic operation of virtual circuit. In the later implementations of virtual circuit, when you book a virtual circuit, they get you to book your route, but they'll also book you a standby route. So if this one breaks down, maybe you can switch the rest of the package to the new. But forget about that. That's an addition. We just want to talk about the virtual circuit. Same with, circuit switching, even though we say it's dedicated, but there's actually a technique called multiplexing that allows you to send a few calls on the same link. But that's just the basic idea of each of those circuit switching, so we don't get too mixed up in between. So, but these are the only two techniques that are available today: virtual circuits or datagram switching technique, whatever it is. The message switching is too old, and the circuit switching is old. The circuit switching is the telephone companies, and they replaced it with virtual circuit. This message switching is the old computing companies, and they replaced it by datagram. So now we have those two techniques, virtual circuits and datagram. And most of the questions are going to be about those two techniques, because they are the ones that are used today. In fact, the virtual circuit has proved to be the faster of the network because of this kind of limited use, the fact that they can block new users, so we don't get too many users. With too many users, they just slow down, and the lines sometimes stop. They say there's no point of slowing everybody down to a halt. So they say, we guarantee you a good quality of service. Of course, you need to first do the call setup, and maybe you're refused at the call setup. So there's a possibility you might be refused. But it's not like the circuit switching where it's a dedicated line, one user. This one's still about 10,000 users. And remember, when we talk about the datagram, don't always say it does not have a good quality of service. No, it can have. When does datagram can have a good quality of service? When does datagram have a good quality of service?
Low amount of users.
When you're on this side, why does datagram can have a good quality of service? When does it have a good quality of service? We say it cannot guarantee a good quality of service, but
main fields, you can push traffic to an area.
no, that's just flexibility in routing. If something goes down, that makes it more robust. So if something breaks down, you don't lose the call like with the virtual circuit or with the datagram circuit. Now I'm talking about quality of service. I mean high, fast delivery. You don't get interrupted when you are watching a video. Sometimes you don't get interrupted. Why? It's using datagram switching technique. No, if everything is working normal. When do you get a bad quality of service? When do you get interrupted in datagrams? When there are too many users. If there are very few users, then you have a great quality of service. You only get a bad quality of service and delay if more users come in and start using the line. Remember, the whole network has a maximum capacity, and the number of users use this capacity. If you have more and more users and you are using too much of the capacity of the network, you actually can cause it to stop. So, which one is better? Now we get back to the same old question. Just those two techniques. Let me get the